So I'd like to talk about the table class and queries in H5ID. So, Lori, do you see the, yeah, you do see it. So this came up in the HSDS forum. Hello, everyone. I'd like to use HSDS and wondering if it's possible to make complex queries similar to what we can do with pi tables. And that reminded me of a blog that Andy Skopatz posted a few years ago, Python and HDF5 a vision. And it was this idea of a kind of merge between pi tables and H5Pi. So some background, pi tables and H5Pi are both Pythonic wrappers around the HDF5 library. Pi tables takes a little more of a distinct view, whereas H5Pi is more of a straight to Python vision of HDF5. Pi tables has features that are not found either in the H5Pi or the H5 library. For one, there's this ability to do queries across datasets. Anyway, so fast forward a few years. In H5PD, which is the Python client library for HSDS, we actually have incorporated many of these features that Andy envisioned for this H5 for the H5Pi pi tables merger. So let me jump in to a notebook. So this is on GitHub. I'll post a link in a bit so you can try this at home if you want. So let's just run through this. So we're going to import H5PD and pandas and matplotlib. And then I'm going to open this domain, smp500.h5. And you can actually download this from S3. So inside this domain, there is a data set called imaginally dset. So let's grab that. And we see it's not actually the H5PD dataset class, it's the H5PD table class. And what is that, you may ask? Well, table in H5PD derives from dataset. So it inherits all the dataset methods, plus a few extra methods that are particular to tables. And by tables, what I mean is one-dimensional datasets of compound type. So basically, you're thinking of rows of data and where your columns are field names. And you can see an example of this in a second. So this data set has some 3 million rows. And the data type is, let's see here. We have date, symbol, sector, open, high, lows, volume. So as you can imagine, this all come from market data for the S&P 500 stocks over a span of many years. And it actually starts in 1970. So if we grab the first 10 rows of this table and then print the date column, we see it's like 1970, 01, 02, 1970, 01, 02, blah, blah, blah. And if you get the last 10 rows, it's 2015. So January 2nd, 1970 to November 20th, 2015. So this, there's some 500 stocks, of course. And what if we want to get just the rows for, say, Apple stock? Well, we could just read every row of this data set and throw out all the rows that don't have symbol equal to Apple, or we could use our fancy query method. So let's see how this works. So the query is symbol equals AAPL. So it's a little bit of weirdness because this type, symbol type, is basically a fixed string. So you need to put a B, means bytes. So you say dataset read where query. So for this dataset, give me all the rows where the symbol is equal to AAPL. So we run this and returns in 1.05 seconds. And we get some 8,813 rows. So this is likely quite a bit faster than if you had to read through each row turn by turn. And if the server happens to be far away from the client, there's additional benefit in that less data is getting moved between the server and the client. So there's a few wins in efficiency. And the way the query operation is actually implemented is that we take advantage of all the DN nodes in HSDS. So for a large data set, it'll traverse many chunks. And it's likely that at least some chunks belong to each data node. And the query operation basically broadcasts this query operation to each data node. Each data node in turn then does a query for its set of chunks, return those to the service node, which then returns the final result to the client. So let's take a look at this. If we cast it to a pandas data frame, we can see this more nicely, right? So you have index, date, symbol, sector, open, high, low, volume, close, and then our rows from 0, 1, 2, 3, 4 to 812. And we see we have symbol AAPL for each of these. Okay, so that's kind of convenient. We could actually modify the query to do a logical combination of different conditions. So here, I'll flip this query to be symbol equals APL, and the open is greater than 100. So you want rows that have the symbol and any open value that's 100 or greater. So we can run that. And then in this case, we have just 280 rows are returned. And if we do a pandas data frame, we get something like this. So we see our first open is 100.70. All right. So let me go back to the original query now. And run that. And see that. Oops. What did I do? Okay. So there's our data frame. And we can do some kind of fancy financial calculations, get a moving average, and make a plot of that. Okay. So that's good. And then here's this pandas describe, gives you some useful information like mean, standard deviation, min, so on. Here's another trick for you stock analysts out there. Let's find the largest one-day gain for any stock. So here again, you could read every row, and that's basically what we're doing here. But we're going to use a kind of like a database kind of syntax. We say cursor equals dset create cursor. And then for row and cursor, we'll calculate the gain as difference between high and low. And if that's bigger than our max, we'll set the max to that. And then copy that to our target. So this is better than reading row by row because when you say for row and cursor, it's going to batch downloads from the table. Okay, it won't grab everything at once to save memory, but it won't just read one by one. It'll find some efficient number of rows to download so that you reduce number of round trips between the client and the server. So let's try that. So this takes a little bit longer. And then we're reporting that the max gain was, what was the gain? Okay, it was here, was between 486 was the close and 422 was the open, I think. So good. So if we had bought the stock that day, we would have done really well. Any other questions on what I've shown so far?
Or also any HDF5 questions too we could take.
John, I'm sorry, you may have already covered this. It was a little late. Is the readware not part of the plain vanilla H5Py?
No, it's part of Pi tables, but not part of H5Py. So that's why I was kind of explaining there's this desire to kind of merge features of H5Py and Pi tables in some fashion. And that never got accomplished. But in H5PyD, at least, we have partially gotten there by bringing some of the Pi tables features into the H5PyD world.
Ah, I see. Okay. All right. Thank you for that explanation. Okay.
And I'll say one thing, going back to Pi tables. Pi tables does use what's called indexing. And in indexing, you create an ancillary data set to make these kind of queries faster. And we chose not to do that with H5PyD, partially because we didn't have time, and partially because we found that for really large data sets, the amount of storage you need for indexing can become problematic, right? Depending on what you want to index, the amount of indexing data can be as large or larger than the data itself. So instead, we chose to take advantage just of the parallelism of HSDS to get the best performance we can with the minimum amount of storage required. So I have another notebook example here.
Oh, John, one other question, but regarding when you talking about the merging of some of the features of Pi tables, there isn't any real technical limitation to doing that for H5Py. It's just it hasn't been done, but it could be, just as you have done it on the H5PyD side.
Right.
Okay.
And they started the work to do that, as I recall, but I think they did run into some technical issues. I don't think they're insurmountable, but it just turned out the amount of work required to do that was more effort than anyone had time to contribute to it.
Yes. Okay. But there were no real showstoppers that you probably couldn't have worked through given enough time and resources.
Right.
Okay.
Okay. So next, in the first notebook example, we're showing how to use query operations to read data. But you can also use query operations to write data. And let's see how that works. So again, we'll do this import. And this time, I'll create a new domain from scratch. And I'll find a data type that is just a 1-byte integer followed by a 4-byte integer. And my thinking was to use this first field as kind of marker of rows that have been modified versus rows that are still in their initial value. Okay, so there's a group function called create table. Just like create dataset creates a dataset, create table creates a table. So let's do that. And you'll notice that whereas create dataset takes a name, a shape, and a data type, here we just provide the name and the number of rows. So I want 0 rows, and we get a 0 shape data set. So this is rows. Oh, here, let me clear all this. And the shape. So n rows is an integer, so it's 0. Shape is a tuple. So data.shape is accessing the dataset property, whereas data.nrows is accessing the table property. So a table is still a data set, so you have all the same data set properties, and simply that the data set shape is a tuple, but for a table, there will always be a tuple of one element, if that makes sense. Okay, and if we do dataset.chunks, we see that the chunks is 262,144. So why that? Well, HSDS always tries to set the number of chunks, the size of each chunk to be around 2 megabytes. And so here we have a data type where each element is a little more, is 5 bytes. And so to get around 2 megabytes, you would need this many rows. But wait, you say, I only have 0 rows. Well, you don't know that this table may expand, definitely. So to come up with something that will never be less than 2 megabytes, we just initially set this chunks value. Okay, so a new method in the table class is append. So append says you can add 1 or more rows to your table. So that's kind of convenient. In H5Py for a data set, you'd have to first extend the data set and then add rows to it. Here, we can do it in one operation. And there's another slightly tricky aspect of this for a multi-reader, multi-writer application. Imagine you have a bunch of workers and they're all busy doing table appends. You wouldn't want, say, you extend the data set, you find some new space to write something, you write that, but between the time you expanded the data set and time you wrote, another worker had already filled in your slot, right? That would lead to some unexpected results. The way that the append operation is implemented is that the append in one atomic operation would extend the data set and fill in those values. So there's never this problem of where you're attending to write data not being where it should be. Okay, so we did a data append and we had data 0 now is 1, 42. And then if we go back to data n rows, that is 1, no, to actually run this. So now it's 1. So let's do this next. So I'll do 1,000 iterations of this loop where I get a random integer between -500 and 500, and I'll append 1 and that random integer to our table. So I run this. So this is actually a little bit slow. It would be more efficient if I didn't just do 1 row at a time. I appended, say, 100 rows at a time. And now we do data in rows, and it's 1,001 because we appended 1 row and then we appended 1,000 rows. Okay, so let's go back to our query function. So some number of these will be less than 0, and some number will be greater than 0, because our range for the random integer was -500 to 500. So let's see what that is. We'll do a read where value is greater than 0. So it's 515, right? You wouldn't expect it to be exactly 500 because there'll be random fluctuations every time you run this notebook. Okay, but let's say now we decide we don't want, we want to zero out all the negative rows. So I want to keep every positive row where it is, but any negative row, I want that to be 0. Well, I could, again, do this iteration loop and read a row. If it's less than 0, set that row, and so on. But instead, I will do this update where method. So update where takes a condition and a dictionary. So the dictionary says what fields I want to modify if the condition is true, and the modification value. So here I'm just setting the value field, and I'm leaving the isSet field as it is. So we can run that. And this returns all the elements where the value is less than 0. So 485. And now if we do a read where value less than 0, hopefully we'll get 0. And that's true. If you can say less than 1, we should get all the 0 elements. And yes, we get 486. Okay, so it's kind of interesting, right? Again,
Are all the methods atomic in the same way that the append is?
yes.
Okay.
And again, the one advantage of this is that you don't need to trundle the data between the server and the client. You just tell the client, just tells the server, do this operation, and all the data reading from storage and modification and writing back to storage happens server side. So that's efficient. So you could even use this kind of method to create, say, a queue, right, where you have you write data in and you read data out atomically. So that opens up some interesting possibilities. So that's about all I was prepared to say for the table class. I think a lot of people haven't come across this as of yet, so I really hope that now people are aware of it, they can try it out and provide some feedback and let me know things that work well or do not work well. So any questions about the table class?
John, where's the description for the syntax of your statements?
Well, that brings me up to another issue, is that we've never created a really well set out documentation for H5PyD, right? And mostly, it's sufficient to use the README and just refer to the H5Py read the docs for the H5PyD documentation, since most of the properties and methods are just identical between H5Py and H5PyD. But then we come to this kind of area where there's new functionality in H5PyD, and that approach is clearly lacking. So what we're intending to do is to create a new set of documentation specifically for H5PyD, and that'll come out on our next release. Right. Till then, your best approach is just you can look at the PyTables documentation and also just play around with the examples. And if anything is still confusing, of course, you're welcome to go to the HSDS forum and post your question there.
Okay. So in the interim, the pi tables statements, the pi tables documentation is going to be a pretty good guide.
Right.
Okay.
Yeah. And it's also the same method. It comes from NumPy.
Okay.
So NumPy is basically a package for working with arrays in memory, whereas HDF is working with array data and storage. But H5Pi has the approach of basically applying NumPy syntax wherever possible to the HDF operations. So this approach is kind of extending that for methods in NumPy that weren't part of H5Pi. So there's a NumPy array read where method. This works the same way as NumPy, except instead of just reading an array in memory, it can read the array from HSDS.
Okay. Got it.
All right. So any questions about anything at all?
I have a question about HSDS. I work
Sure.
closely with the NASA's Goddard Space Flight Center, and we do satellite processing.
Sure.
A lot of the data stored in HDF5, and one of the aspects to it that's important to us are the cryptographic checksums of the files. We transmit these files around. We have to keep track of those just to track the storage, but also to make sure that they arrived at their destinations intact. Which of course that means that now the order of the bytes in the file is important. Any rearrangement of that changes that. And I guess HSDS would kind of dispenses with that, right? Because the individual data sets are stored as objects in an object store, as opposed to a particular string of bytes.
Right. But we do provide a checksum of sorts. If I don't know if you guys can see my screen still, but
Yeah.
So if I do, there's okay, let me start with edges. So the file we had to start with was home test user 1 S&P 500 H5. Right. And that just lists, okay, there's one object, a data set table, and it's 3 million rows.
Now, when you call that a file, what you mean is it's a
domain, right?
It's
Sorry,
okay.
sometimes I slip and I say
Right.
file and I really mean domain.
Okay.
And what's the difference? Well, the storage model for HSDS is basically sharded. So each object and chunk is a separate, relatively small object within the storage. Whereas in HDF5 library, all those things are within one POSIX file. So there's another utility called HSDAT. And if I do the same deal here, it provides some interesting information. So I think what you might be interested in is an item called MD5 sum. So this is just a checksum. And how it's computed is that we do a MD5 checksum of each object, and there could be millions of objects. And then we do basically a sum of those checksums. So if any dataset value, any attribute, any link changes in this domain, the MD5 sum would change. So it's like a guarantee that if you copy this checksum and you see it doesn't change, then the contents of that domain haven't changed.
And so I gather these domains are, I don't know what you would call it, hosted on a particular system, and
right.
And you could transfer that one domain from one host to another.
Yes, there's a utility called HSCopy. which copies one domain to another. So you
And
can
the-
do that from local to a
Right.
host or host to host, etc.
And the expectation is that the MD5 sum would be the same even after the copy.
Correct.
Right.
So yeah, and so maybe if you have any follow-up questions, feel free to contact me or
Okay.
again post to the HSDS forum.
All right.
All right. Anyone else have questions? All right then. So I'll have Lori post the various links to notebooks and such. And it's been nice talking to everyone.
Great, thank you, everyone. We'll see you next week.
Thank you. Bye-bye.
Bye.